All right, so let's see. Your assignment number 1 has been released. You can check the deadline on the instruction PDF. And assignment number 1 is actually about regular expressions, epsilon, NFA, which I'm hopefully will cover today. So pretty easy stuff, simple stuff. I shouldn't say easy, but simple stuff that you already learned from 2001, but we'll definitely review them also today. So that one's going to involve about regular expression and also epsilon NFA, and also about their conversion. Take a look at the instruction PDF and also import a starter project and start coding. I think that one's a pretty good Java coding exercise, for you. It's not difficult assignment, but I think it definitely can let you kind of see a little bit about transformation, which will be more or less what you will have to do somehow for your project. You got to create your own classes, and then you got to do some transformation yourself. That's something you will have to do. But anyway, so get started with it as soon as you can. And on Thursday, I can talk a little bit about some essence of the assignments. But for the details, you will have to work it out yourself. And on the lecture side, I already got the review slides on the math, propositions, sets relation. Take a look, and then I think they're useful stuff actually for your understanding of quite many parts for this course here. And then also optional, let me just show you once more where you can find this. This is the tutorial videos on Antler 4 that you will be assigned at some point closer to the reading week. But if you really want to get a head start, you want to give yourself a little bit more balanced workload before the reading week, be my guest. You can go ahead and do it. Right? So it's under tutorials of the lectures page and then Antler 4. All right, so that's the first one there. All the tutorial videos are relevant. So you may want to, gradually go over them, take notes, and then it's going to save you tons of time later for the lecture, later for the project. All right, so that's about what I want to say. Any questions about the course? All right, awesome. All right, let's now recap very quickly, and then we'll move on to epsilon NFA and also how we can convert from regular expression into epsilon NFA. And then we're almost towards the end of the lexical analysis. Not yet, but almost. Okay. So last time, we actually spoke about how you can process the string character by character using NFA over here. And because of non-determinism, we have to make sure all the states from each character processing is going to be a set of states. Right? It's just the nature of the non-determinism. So we also spoke about non-determinism in different occasions. You guys can review about what exactly we discussed. Right? You can also take a look at this exercise over here to see why it should be rejected. You want to really pay attention to this Boolean condition over here. So this set of states will be the ending states after processing 1, 2, 3, 4, 5 characters. Right? So it's the ending states, which will be a set. And this will be the result, this will be the accept states right here for this NFA. If these two sets are not, if their intersection is not empty, that means at least one of the states over here is accept states. That's the interpretation. So think about this Boolean condition here. So this condition tells you that the string that you have processed either have to be rejected or you have to be accepted. Right? So that's something you want to pay attention to. And then we spoke about different alternative to actually writing this Boolean condition. This is what you will see on the slides. This is something extra I gave to you guys, right? You can think about other alternatives that might be valid. I think some of you also suggested something else which would not exactly work. We also go over why they wouldn't work. And transition function, right? So the delta symbol is actually, well, I would say there's an essence of defining what a machine is. So when we talk about deterministic versus non-deterministic, the difference really is, in the case of determinism, you are only returning a single state for every transition. So it's guaranteed just a single unique state you're transitioning into. On the other hand, for non-deterministic machine, you're going to get a set of states, right? So guys, you got to make sure you also review the math review slide about what power set is, right? So I actually cover quite a bit of a power set kind of stuff and exercises in that slides. Take a look. Okay. And, oh, by the way, so I just noticed that. So we also talk about the different conditions for non-determinism, right? That's kind of the different occasions I spoke about. Please go over them. If you want extra explanation, you can see the recording or reach out to me, we can talk. And this diagram here really try to relate about DFA and also NFA. So we are saying that DFA is actually a more specialized version of NFA. That means every DFA is actually a NFA. On the other hand, not vice versa. Not necessarily every NFA is actually a DFA. For example, in case the NFA actually got some non-determinism, in that case, it cannot be a DFA, right? So you can also go back to the lecture from last week, last Thursday, and see the details, right? But this diagram here is actually very important to relate the two machines. And of course, once you, if you're given some NFA, you can convert that into DFA. That's basically the last conversion that we spoke about last time, right? I'm going to recap as well. Just go over with you very quickly. Okay. Just before that, we talk about formulation of NFA, right? So it's pretty much similar to how we kind of define recursively the transition function for DFA. So for that part, I can let you guys study the math. But I just got to remember, every, for example, the base case for NFA is going to be a set of singleton states, not just Q, right? Just notice that every state here should be a set, okay? And then we spoke about the, let me see, yeah, right here. Oh, sorry, right here, beg your pardon, right here. So that's the equation you will see actually in the slides. I also work out from the beginning, with you guys last time to see how exactly to understand this set comprehension. Take a look, and then we'll see something that's even slightly more complicated about NFA. We'll get there, okay? Beg your pardon. So this is NFA, and we're going to see something even more complicated with epsilon transition in the place. That's something we'll see today, right? Very similar, but just with some slight extension. But the way we define a recursive case is to really break the string into the prefix and the last character. That pattern there is really the same, right? Very standard pattern, okay? And then we talk about the generalized union operator, and because that one there is actually used right here, right? So you can also take a look. That will also help your understanding. I don't think the generalized union operator is in the math review lecture. That one might be missing. So, but you're here, right? Right here. So you can see that too. Right? I believe that's the last page that we spoke about last time. Let's just go over them very quickly, right? Just to brush up your memory. The problem is follows. We are given some non-deterministic machine over here. You can see that if you got 0 here, it might go to either state, right? You got multiple possibilities, so it's NFA. Our goal is to transform this NFA into the corresponding equivalent DFA with determinism. That's what we want to do. So this is the ultimate DFA, and you can also see the neater diagram on your slides, right? So that's the ultimate DFA. And one thing that's very important to note, if you look at every state in the corresponding DFA, every state here corresponds to a set of states in the NFA. For example, you can see Q0 here corresponds to just a singleton set consisting of Q0. On the other hand, let's say Q0, Q1, this is what we call a subset states. You will actually see that term in the slide, which I also mentioned last time. So this is a single state that corresponds to a subset of the states in the NFA. Q0, Q1 simply correspond to the possibility of reaching Q0 or Q1. And we're considering these two as a single states in the ultimate DFA, right? It's a very important insight to actually remember, okay? All right, so let's now talk about this table here, right? The way you build up this table, of course, is from scratch, which we did last time. I think you will get a chance to see another similar kind of a lazy evaluation construction today when we try to convert from epsilon NFA into DFA. The procedure is very similar, except for one single extension we have to do about epsilon transition, which we'll talk about today, right? So for this one here, we start with this here. So Q0 corresponds to the single start state in the NFA. In the corresponding DFA, we simply make Q0 a singleton set because every state in the resulting DFA is simply a set of states in the source NFA. Just remember that principle. And we only try to add a row when necessary. And that's the algorithm I'm also going to go over with you very quickly, so you will see exactly how this can be implemented in the actual coding if you need to. Okay. So for every one of them, so let's say Q0 here, that's the only one that we had to start with. In that case, we simply apply the regular delta, which will take a single character, which can be either 0 or 1. We're assuming that the alphabet is simply 0, 1. So we can either go this way or that way. And then you got another set of states, you got another set of states. Now, these two are different in their nature. We start with this one here, and then we reach to itself. So this corresponds to start with this one here and reach to itself, like a self loop. That means we don't really need to add Q0 to another new row anymore, because that one there has already been defined in the current row. On the other hand, if we are here and we process 0, we're going to get to a new so-called subset states, which will consist of Q0 and Q1. So that's why from here, you will see that by reading 1, we're going to a new states, which consists of Q0 and Q1, Q0 and Q1. So to really figure out exactly what's going to happen if we got 0, what's going to happen if we got 1, we'll just add a new row accordingly, here and here. All right. I call this one to be discovered. That's really the name. I kind of call that in the algorithm, which I'll go over with you. All right. So I kind of go with this kind of lazy evaluation in the sense that you only go to the subset states whenever necessary, until the point that if both states over here, for example, both this and this are already, so for example, this has been already discovered and this one has been already discovered, you don't need any additional subset states. So that's where we stop. All right. Any question about this lazy evaluation? Good. All right. Maybe that rings the bell, maybe from 2001. If you haven't learned it before, now is the time to learn it. All right. So now for today, I would like to start with the algorithm about lazy evaluation very quickly, right? The actual coding, you will actually have to go over the pseudocode yourself, but I will help you read it quickly. We'll just do a little bit tracing, just for one iteration. I think that'll be enough. So what we're talking about here is slide number 40. All right, so the input for the algorithm is an NFA with non-determinism. And the output eventually is actually the output here, right? We got input and also we got output. Output is going to be some DFA. But exactly how do we do that? All right, let's now go to the algorithm. Okay. You want to pay attention to two variables here. So the algorithm itself is called reachable subset states. Just to start with, if you think about the Q of the input NFA. Okay, so if you just go back here, so this is the input, for example, that we were talking about. We got Q0, Q1, and Q2, right? Let's just Q0, Q1, and Q2. Q0, Q1, and Q2. There's one insight which I didn't really mention last time. Let's now talk about it. Since we know that every state in the corresponding DFA is going to be a subset of states, right? That's all we talk about. Now here's a question. What's the worst case for the DFA? What's the maximum number of states you might get in the ultimate DFA? To really figure that out, okay, let me write down the question first. Now, the question is, what's the maximum number of states in the output DFA, potentially? What's the upper bound? Okay. To really see the upper bound, basically you want to see how many possible subsets are there for out of Q0, Q1, and Q2. Basically, that's what you want to see, right? To answer that question there, the result will be the number of subsets from the Q of the NFA. So I say Qn over here, N here stands for the NFA, right? That's what we talk about. How many subsets do we have? This actually relates to a math review lecture, but I'll give you the facts over here. If you got Q0, Q1, and Q2, how many subsets do we have, really? Okay? You can think about somehow we are trying to construct a set out of Q0, Q1, and Q2. For every element over here, you have a binary choice, either to include it or not to include it. And for this one here, to include it or not to include it. So this one here, to include it or not to include it. In that way, you got two choices, multiply two choices, multiply two choices, you got 8 choices. Let me just show you a little bit more, okay? We're thinking this way. So if you got, let's say, Q of the N of A, Q0, Q1, and then Q2, okay? Let's say to include it with, say, digit 1. To exclude it with, say, digit 0. So basically got 0, 0, 0, 0, 0, 1, 0, 1, 0, right? Etc. All the way to 1, 1, 0, and then 1, 1, 1. All right? As you know, this one corresponds to the number 0, number 1, all the way to 6 and 7, right? Just from binary to decimal, right? Just for you to see. And what does this really mean? That means not to include any one of them. So this will be corresponding to the subset of empty set. And this one will correspond to just include Q2. And then this one here, just include Q1. And what about this one here? Include both Q0 and Q1. Q0 and Q1. So that one there, Q0 and Q1. And the last possibility will be to include all of them, Q0, Q1, and also Q2. So this is about the theoretical upper bound, about the number of states that might appear in the ultimate DFA. However, we don't necessarily want to go with this route because 2 to the power, well, if you think about it, so here, the cardinality of the Q of the DFA, corresponding DFA, could be up to 2 to the power of the cardinality of that. Right? You can see the cardinality of that is actually 3. So 2 to the power 3, we got exactly 8. Right? We can get up to 8 states. Imagine that if you actually got 10 states in the NFA, so what's the upper bound? 1024. Right? So that's not the way to go. So that's why I didn't really show you this back on Thursday. I kind of show you the lazy evaluation right in the beginning. So lazy evaluation is the way to go. Typically, if you do lazy evaluation, the actual DFA you will get it actually has way smaller number of states. This one here is the theoretical maximum. Theoretical upper bound. Practically, you rarely reach that. You may not reach there. Practically, may not reach there. Instead, we want to use lazy evaluation. For example, you can see here, if you go back to our result from last time, you can see Q0, Q1 is here, but Q0, Q1, Q2 is not a state over there. That's simply not reachable. So we don't even bother to put Q0, Q1, Q2 as one of the rows because it's simply not reachable from the initial states. All right? So the remark I'm going to do is like this. So Q0, Q1, for example, is reachable if we use lazy evaluation. On the other hand, the Q0, Q1, and Q2 should be there in theory, but practically it's not there because it's simply not reachable. It's just a very small account about between if you go for the maximum number of states to really consider versus you just go for lazy evaluation. Okay? So the algorithm that you will see over here on slide number 40 goes with the lazy evaluation. You only add a new states in the DFA when necessary. Okay. All right, questions about this? Yeah.
We have Qn.
Yep.
The capital N. Can we put in this case Q3 or something? Does that represent the number of states in that set? Or
are you talking about adding Q3 to here? And here?
Yeah.
Oh, here, just a naming, right? So here, I'm just saying the set of states in the NFA. That's what I'm saying.
Oh, in the NFA.
In the NFA, yeah.
Okay, got it.
Yeah. You know what? This one, the name here really doesn't matter that much. So to avoid confusion, I can simply say NFA. And the NFA I'm talking about specifically is really this NFA right here, with 1, 2, and 3 states. Just one example. Okay, good? No worries. All right, let's take a quick look on the algorithm. Right? We don't need to spend too much time. But given that we're going to talk about only reachable, right? That's the lazy evaluation part. So we only get to a subset state when necessary. Okay, reachable. So this is the lazy evaluation part. All right, so here I'm including the table that we worked out last time, just to show to you. I'm going to trace this algorithm slightly, but just for the first iteration, for you to get an idea. You can feel free to maybe trace the rest of the other 2 iterations. Okay? So before the loop, we have 2 variables here. So you're going to pay attention to them. So we got something called reachable, and we got something called toDiscovered. All right? You can think about toDiscover. Once it gets to be empty, then we have to terminate the lazy evaluation. Okay? So toDiscover over here, you want to pay attention to how it is used right here. So while toDiscover is not empty, we keep going. As soon as it becomes empty, then we exit from the loop. As soon as toDiscover becomes empty set, exit from the loop. Right? That's a very important insight about this algorithm here. So you will see that for each iteration, we somehow have to update both the reachable and also toDiscover. But in the very beginning, even before the first iteration, we're going to say all the reachable state is just initial states, Q0. And to really start the table, we start with Q0. All right? So that really corresponds to this part over here. All right? So that's really our starting point. So here we're saying that the starting point over here is Q0. Reachable is Q0. And also, the toDiscover is also Q0 right here, right? We're saying just start with that, right? And because the toDiscover over here is currently not empty, it contains Q0 subset states to start with. So we're going to go into the loop, the body of the loop. The first thing we do is to be sure, since now we are considering Q0, that one is not to be discovered anymore in the next iteration. So that's why you're going to see we choose anything from toDiscover. And then we're going to remove that thing, which will be the current row, from toDiscover. Right? That's what we're doing. So think about this line here is actually going to this line here. So this one here, for the very first iteration. For the first iteration. So the S to be chosen, we have no choice. Basically, you will only choose Q0. Choose S, Q0. And then, after that, we're going to remove the toDiscover. toDiscover becomes, what's going to happen after we try to remove Q0 from here? Becomes empty, which is okay. Because by the end of the iteration, we are somehow going to add this one toDiscover, which will be okay for the next iteration. I'm just doing a little bit preview. All right? Becomes empty. Okay? This is only in the beginning. And then, now we are going to see how we can update these 2 variables. Not yet discovered, over here, and also reachable. So these 2 variables ought to be somehow updated. Oh, beg your pardon. So this is just another variable. We're going to update this one here at some point, and also update this one at some point. We'll get to there just one moment. But we need some intermediate variable. Okay? The intermediate variable basically is to say we want to somehow get, let me just get there first, and then I'll show to you. So this is not yet discovered. Okay? Not yet discovered is going to be a set difference. So this one here is set difference. Basically, whatever contents we got from this set here, minus those in the reachable. At the moment, reachable contains only Q0, right? At the moment. Okay? And now, if you look at just this part carefully right here, all right? Let's see the correspondence very quickly, right? You can see we are basically applying the transition function, delta, and also delta over here. And we are considering input character 0 and input character 1. This part here, you can see the correspondence right here. 0 here, 1 here, 0 here, 1 here. All right? And then the S that we are talking about currently, right here, is really Q0, right? So we are really talking about Q0 and also Q0. We want to see what happens if we go from Q0 and taking 0, go from Q0 and taking 1. So that's exactly how we figure out this set here and this set here, right, from before. Right? Okay, and then we're going to union these two sets together. So what do we get? Okay, so just this part here. Okay, just let me go with this. This part here is going to correspond to Q0, Q1. And this part here is about the right-hand side when we try to process 1. Right? Exactly how to apply the transition function, we spoke about it in detail last time, so I'm not going to repeat it. You can refer to the recording if needed. And then this part over here is going to correspond to Q0. Okay? Okay, so let me just show you very quickly the computation here. So not yet discovered. In this case, it's going to be Q0, Q1, and also Q0. And I'm saying union them together. Okay. And then, oh, by the way, this is set comprehension, right? Set comprehension. So that means there's a little bit more detail here. So you can think about this one here. Okay, I'll just make a little bit more space. This is one set, and this is one set. And this one here is simply a set with two members. So this one here is really a set with Q0, Q1, and also Q0, right? That's what we are doing. And then we got the set difference. What's the reachable right now? Q0. Right? So that's really what's going to happen in the first iteration, precisely. Okay? That means in order for us to find out what's really not yet discovered, whatever that's already reachable, they should be taken out from here. So we only got Q0, Q1 left. All right? That's the only thing we got left. And that one there is actually going to be equal to Q0 and then Q1. And this step over here really corresponds to what we said last time about when we actually calculated Q0, Q1, this one has not been discovered, so we're just going to add it to the next new row. Right? That's pretty much what you got to do for the first iteration. So once we calculated not yet discovered over here, which is going to be Q0, Q1, we're just going to update reachable and also to discover accordingly. Right? So these are the two places you can also trace by yourself. But I think the most important part is about how to calculate this variable here. And once you have done that, you can update the reachable and to discover. For example, for to discover here, remember in the beginning, to discover becomes empty, right? But now we can add this guy here to the empty. is going to go from this one here into Q0 and Q1. So this would mean when you go to the next iteration over here, when you want to choose this, you can choose exactly this, which will correspond to this. And then you go on with the next iteration. Okay? I'm going a little bit fast over here, but that's really corresponding to exactly how we did it manually. We're just trying to specify some algorithm to automate it. Right? Any part you want me to explain a bit further? For you, we're okay. Go ahead.
I know you explained it already. Why did we have a set within a set?
Set within a set, yes. So if you look at this one here. Okay. This one here is going to tell us about the resulting states after processing 0. In this case, it would be exactly Q0, Q1. The reason that we are enclosing this with another set is because imagine this. If we didn't have this, I'll show you exactly. So if we got Q0, Q1, union Q0 versus Q0, Q1, union Q0. That's really the difference, right? Let's see exactly what's going to happen. This one here is about the states after processing 0. And this will be the resulting states after processing 1. What will be the result after the union? Q0, Q1, that's it. Versus, if I put this in a separate set, this is a member of a separate set. That one there is going to give us something different. Q0, Q1, and also Q0. You can see somehow we preserve the subset state here and preserve the subset state here. So we can somehow, actually try to remove the one that's already been discovered, right? It's a good question. I think the subtlety here is really important, right? So this is the way to go. Okay? Good. All right, so the algorithm, I think you'll be good for today. You can study that a bit, and then if you got any questions, let me know. Okay, and I'll leave that to you. Okay, it's a pretty simple algorithm, but it works pretty well. Okay. So now we're done with the NFA. Let's now try to extend it and talk about something called epsilon NFA. All right, let's talk about it. And let's start with some motivation. Right here. Epsilon NFA really is to extend the NFA by a so-called epsilon transition, meaning that I can just transition to another state without processing anything as an input. Okay, I'll write it down. Epsilon NFA basically allows an epsilon transition to another state without reading anything. You can just jump directly without reading any input. And the way to visualize it would be, normally you would write a transition like that, but you just say epsilon. So you can easily go from maybe some S to T. If I'm here, at the same time, I can also be T as well, S and T, right? Because epsilon tells me that I can either be in S, but without reading any input, I can also be in T. I can do the transition right away, epsilon transition. You'll see a little bit more formal definition just a little bit later. But let's see how useful this can be, all right? Let's say you cannot use this epsilon transition. Imagine how you're going to use the NFA or DFA. You can be my guest, choose the one you like, to really specify a language, to specify either DFA or NFA that's going to recognize this language here and this language over here. Let's see what they really represent very quickly. This, again, is a set comprehension. We're saying that every string in the language is going to be a concatenation of two things. So we got concatenation between x and y. X over here is just going to be alternating zeros and ones, which we did earlier. And it's going to be concatenated with one part of y that has odd number of zeros and ones. So think it this way. If this is my input, this is my string w. Somehow I can break it down into two parts. And this part over here, I have alternating zeros and ones. And this part here, I got odd zeros and odd ones. Any string that will satisfy this pattern here can be included in the language. So now the question is, how can you do it in DFA or NFA? You can do it, but it's going to be complicated. Okay? That's one problem here. Another problem will be, let's say W here is just any string, right? Any string such that W either has alternating zeros or ones, or it has either odd number of zeros or has either this or this. So thinking this way. So this one here, given any string W, I will accept W if either it has alternating zeros and ones, alternating zeros and ones. If no, that's okay. I can check the same string to see whether it got odd number of zeros and also odd number of ones. So these two patterns don't need to exist at the same time. As long as one of them exists in the string, I should include that string in the language, right? So now again, you can think about how you may actually draw a DFA or NFA for this. Okay. Right, so that's kind of the problem we're given. And you should really find that to draw the DFA or NFA for each one of them is going to be quite complicated. But it's not feasible. It's not infeasible. It's definitely feasible because they are still regular languages. But with the epsilon transition, you can actually somehow divide and concur for this problem here. I'll show you. So we already solved this problem earlier about having alternating zeros and ones. If you can somehow get this one here, it's a diagram. So this will be the DFA or NFA. I'll just say NFA here. For alternating zeros and ones. Just get that one drawn first. That one there, if you recall, has a single start states. Also, it has two accepting states. One here and also one here. Right, if you recall. And the details you can fill out. Okay? And we also know how to draw this one here. And that one there also has, that one there, let me just use a different color here. That one there, it's just going to be another diagram we can draw separately. That's why I said divide and concur. That one there can just another NFA that's going to give you odd number of ones and also odd number of zeros. And that one there will also contain also one accepting states. That one you can also draw very easily, right? That one there also has a single start states and a single accept states because you got to be n. Let's say I can draw these two separately. How do I make them into one machine? In the case of DFA and NFA, you cannot do that because every time if you want to say I want to concatenate x and y, I had to read something from the alphabet. But in the case of epsilon transition, you don't have to. So the way we do that will be, we can now make this one here the start states. And then from this accept states, oh, I forgot to draw one more thing. This will be the start state for here, all right? I can say after that, I can simply transition to here by using epsilon. Also, I can transition to here using epsilon. So this part here is really the x. And this part here is really the y. You can see it's a very clear divide and conquer. I divide this task over here into x and y. X will be recognized by this, which we know how to do. Y will be over here, which we know how to do. And then we can somehow concatenate these two by using just epsilon transition. All right? That's one. The other one, kind of similar. So let's say we got another thing here. Okay? So let's say we got here, and also we got here. Okay, for the first one, alternating zeros and ones. So this will be, what would you say, NFA1, which will have 1 star states and also 2 accept states, right? 1 here and 1 here. And also this, let's say, is NFA2. Okay, 2. Also, we got 1 star states and also 1 accept states. Now, how do we somehow express? We can accept either way. The way to do that is, well, you can simply say, why don't we let this one to be the star states of some epsilon NFA? And then, since we say we can accept either this or this, we can either go for epsilon transition over here, or non-deterministically, we can also choose to go here, as long as one path is going to lead us to some accept states, then we'll be okay. That's exactly how we do it, right? So the very major advantage of using an epsilon transition is you can somehow do different parts of the machine independently and somehow try to connect them using epsilon transition. Right? That's really the insight into it. Right? Just intuitive sketch, right? Before we get dive deeper. Okay, why don't we do just one example very quickly, and then we'll take a short break very quickly. Okay. So this is also one the example that's on your slides. Okay. Let's take a look at this guy here. Okay. First question. Is this a DFA? If you don't think so, tell me why not. Yeah, go ahead, please. Why not?
For example, Q1 has 0 or 1 that can loop, or 0 or 1.
Exactly, yeah. So guys, you know pretty well. So Q1 here, if I take 0, I can either go for here or I can go for here. There's definitely some non-determinism. Okay, I'll just say no. But for the reason, you should be able to write down. Okay, I'll just say no here. Now, is this an NFA?
No.
Exactly. Absolutely. Thank you. So here from Q0 to Q1, you can see the possibility of epsilon transition, which was undefined in the regular NFA. That's exactly right. All right. This one will be no, but indeed, it is epsilon NFA. It's basically NFA extended with epsilon transition, right? So that's a very easy 3 question for us to figure out, all right? And after that, let me just try to try a few strings to trace together with you, so just to get an idea, okay? So this particular epsilon NFA is going to recognize the pattern for decimal number, fractional number, basically, okay? So for example, first of all, let's start with something that will accept. For example, let's say 0.23 is going to be accepted, right? So you can see here, well, if you look at the language definition here, we're saying that this language is going to accept all the strings that's going to be a concatenation of 1, 2, 3, and 4, 4 parts. Part number 1 is a sign, which can be either plus, minus, or no sign. And the second part is x, which, excuse me, and the x over here could be any combination of decimal digits. And there's a dot over here, just literally, just dot. And the last part, y here, just can be any decimal digit as well. You can see the star. that means if you only got up to here, you're saying that you might accept epsilon dot epsilon. But we don't allow that. That's why we got another condition here to say it cannot be the case that both of them are epsilon. All right? Notice that, right? So here we're saying that you cannot have a fractional number that simply looks like a dot. It's not acceptable. Either you say 23 dot, that's okay, or you can say dot 46. All right? That's something you want to also look into. So really try to convince yourself about how to understand this language definition here. I think we have seen this pattern here more than once. All right, let's just trace very quickly. Let's say the first one, dot 23. So basically, we're going to go to choose epsilon, and then we're going to choose the dot, and then we're going to go 23, right? 2 and then 3. After that, we can simply take epsilon and go to the accept states. That's really the dot 23. So this one here should be accepted. All right. And let's take a look at another one. Let's say we got dot, let's say plus, let's say another one here. Let's say we got plus 46 dot. How about that? All right. So this time we got a sign. So here we got the sign here. So take the plus, and then you can take 4, and then you can take 3. Oh, sorry, beg your pardon, 6. You take the 4, you take the 6, and then you take the dot. Once you get there, you can just take the epsilon, and then you get to the also accept states, right? Final one. So this one is also accepted. What about we just got something which I also mentioned earlier? What about just dot? This one should be rejected, okay? How do we analyze that? So this one here going to be pink, and the one we just did was orange, right? Just be clear. What about this dot over here? So there's no sign, basically, right? There's no sign. So, and then once we get to the Q1 over here, we also don't take any digits. But well, after this, we don't take any digits. We go to the dot. But at Q2 over here, you're forced to take at least 1 digit. Right? So if you really didn't take any digit over here, it's guaranteed there should be a digit forced right here. So now we're getting stuck right here. So it's undefined. So it's not going to be accepted. Okay? So this is also very important to point out to you. At this stage, you will get stuck if no digits is given. So that's why this one here is going to be rejected. Right? Yeah, try to maybe use different strings to really convince yourself about how this particular epsilon NFA is going to work. Yes?
So is there a reason we don't just accept at Q3 and we go all the way to Q5 with epsilon?
It's a good question. A very good question, though. Yeah? You're actually quite right. If you are right here and then you make this accept states, you'll go right away. It's fine. But somehow I think the example, I just want to show you one more epsilon transition, which will be useful when we talk about how to convert from epsilon NFA into DFA.
Oh,
yeah, this is not the most efficient possible, but it still work.
Makes sense.
Yeah, good. Your fellow student's question was, is it okay if we simply get rid of this and just make Q3 an accept state? The answer is yes. The reason I put this extra epsilon transition here just for a little bit easier demonstration for later. Okay, that's the main reason. All right. All right, so I would suggest we take a very short break by taking attendance. Okay. All right, so before the break, we saw some example about epsilon NFA, and also see how we can process the string. And let's see a little bit more. So I think today, the best interest for you guys will be to cover as much for your assignment number 1 as possible. So I do want to reserve the final 15 to 20 minutes just to talk about how you can go for from regular expression into epsilon NFA, which is quite an interesting diagrammatic exercise. I want to do that first. So let me cover a little bit more about epsilon NFA, and then I'll skip some contents and then cover them on Thursday instead. So you can take advantage of today, tomorrow, and most of Thursday before the class to do assignment number 1 if you wish. I can leave that flexibility to you. All right? So just do a little bit here, some basic ones. If you want to formulate an epsilon NFA as a machine, so pretty much the same as before for DFA, for NFA, right? For that part, you can definitely refer to the definition. What we want to really focus on this page will be the transition function, delta. All right, the delta here, because it's an NFA, right? So that one there is basically going to be, so we got some state Q and also some sigma. However, the sigma here, first of all, the sigma itself does not include epsilon. Epsilon, sorry, let me write a little bit better. Epsilon, empty string, is not a member of the sigma. This is very important to notice first. So the way to really define the transition function for epsilon NFA is to explicitly write out the epsilon on its own. So we'll say union epsilon. All right? And that one there is going to, total function here is going to return a set of states. So this part here is just the same as how we define for NFA. Right, that part is the same. You can refer to the definition from earlier. So the new bits is really about, number 1, the alphabets for epsilon NFA does not include the epsilon. That's a common mistake, just remember, does not include it. So we write this explicitly out. So this part over here really corresponds to this row right here, this column, which we can figure out very quickly, right? That's some basic stuff I want to talk about first. So now we're introducing one column there just about doing epsilon transition. Okay? Very easy to see. So let's say, for example, if we're now in Q0, if we take the epsilon transition, what's going to happen? Q0, take the epsilon, we get to Q1. And if we are now in Q1, and do we have any option for epsilon? We don't. In which case, the resulting state will just be empty. All right? It will be similar for Q2 as well. From Q2, we also don't have any epsilon transition. So, empty. But what about for Q3? Q5, exactly. Yeah, that's also the reason why I put epsilon transition here, so we can see a little bit more, right? Okay, so this will be Q5. All right, for Q4 and Q5, you can check, but it's all empty. All right, so 2 things for you guys to remember. Number 1, when you try to formulate a type for the delta for epsilon NFA, remember the alphabet does not include epsilon. And also, you're going to write it out explicitly. So we are introducing an extra column right here. Okay, that's number 1. All right, and then we're going to move on to over here. You know, this is going to be about how we can convert from epsilon NFA into DFA. This one will take quite a big chunk of time. I would suggest maybe in the next 15 minutes or maybe the remaining class for today, let me talk about the regular expression to epsilon NFA first. And then you'll be ready to actually do the assignments. And then maybe I'll talk about this part here quickly on Thursday. Okay? So let me skip a little bit. Don't worry, I'll come back. Okay, right here, regular expression. It's actually quite fun. Lots of fun. Easy, but lots of fun to do the exercise. We'll do the exercise together. So the slides I'm going to talk about now will be here. This one. Okay, slide 51. Okay, let's start from here. Okay, so the way we kind of construct the regular expression is just simply recursive. You got plus, you got concatenation, you got cleaning star. And then So somehow we want to convert from any arbitrary given regular expression into epsilon n of a also recursively. Meaning that we're going to talk about base cases and also recursive cases. Well, we'll talk about each one of them. But let me just go over some principle with you very quickly. And then we'll do some drawing on a tablet. So we're going to see that given some regular expression R, and then we're going to construct, when I say construct, we're going to draw its equivalent epsilon n of a, right? We're going to see that. Such that for the regular expression and the epsilon n of a, their recognized languages are the same set. No more, no less. Exactly the same set. So that's why we said the epsilon n of a, d of a, n of a, regular expression, they're all equivalent notations. It's just about which one might be a little bit easier for you to specify something in the first place. But they can all be somehow converted to each other. All right, so here is some rule we're going to follow, but we can see that when I draw. Number one, for each epsilon n of a we draw, one accept states only one. Okay, rather than multiple, only one. And then somehow you will see exactly, so when we try to do the recursive construction, we don't really draw the incoming and outgoing for the final and also first states. Well, we'll see that. This one is a little bit more abstract. I'll show you the example directly. Okay, one moment. Okay, so these are the three principles. I can verify them as you study. Let's now see right away. All right, so I kind of put everything together in a single table so we can see all the rules. And then we'll do exercises together. Okay, let's see how much time this might take. We'll see. Okay, let me just look at my notes right here. Okay, good. Let's talk about base cases first. Oh, by the way, you can see that here we talk about input. So we want to go from regular expression, which can be this, this, or this. So if you recall, these are all regular expression, base cases. Or it can be plus, concatenation, and cleaning star. From all these regular expressions, from each one of them, we can draw the corresponding epsilon n of a. And from that epsilon n of a, we can convert that into d of a. Once we get a d of a, we can also apply some algorithm to minimize its number of states, which we'll also talk about. Right? So these are good stuff. They will all be connected together very soon. Let's start with the base case number one. If I simply got base case number one here, I got a single star states, I got a single accept states, like that. And the epsilon over here simply tells me that I should be able to accept right away, even without reading anything. So the way to draw that would be, I simply go from start to the end states over here without reading anything. And for the resulting epsilon n of a, I have to make sure it has a proper start state. So I'll put the arrow here. So that's the base case number one. Meaning that I start from here, without reading anything, I might just accept right away. So that's why epsilon should be in its language. Exactly that language. How about this one here? This one might look pretty similar to that. So here is only epsilon, meaning that the language, by the way, the language of the epsilon over here is simply that. Right? If you recall the lecture from regular expression, right? We are still accepting something, just empty string. However, the language of this is actually empty. No strings should be accepted. Now, how should we draw that, right? Let's still start with, you remember the rule, we talk about one start state and one accept states. So what I would do is I'm going to have this right here, and also accept states over here. Now, how do we draw anything in between to say that it accepts nothing? If I draw something like epsilon, it's going to accept epsilon. How can I make sure it accepts nothing? Huh? By having no transition. Isn't that logical? So the way to make this happen is we simply say, let's make this the star states. That's it. So this is a very funny epsilon n of a. Somehow we don't have any epsilon transition because if you do have it, it's going to change the accepting language. So by having no connection whatsoever between the star and n states, no string can be ever accepted. As soon as you get to the star states, you get stuck right away. Okay. All right, so that's the base case number 2. And base case number 3. We have our star states over here, and we have our accept states right here. And we assume that A, well, for example, right? So let's say 0 is a member of 0, 1, right? If we want to say that, we only want to go accept 0. In that case, we just connect these two by that particular alphabet, right? That's what we'll do. So we simply connect these two states by just the A. And make sure you make this one the star states. So these are the 3 base cases. All right? And now the fun part is really about how we construct the epsilon n of a recursively based on the recursive construct for the, the regular expressions. Actually, these two, we have seen them somehow when I talk about the motivation. You don't need to worry. That's something you can refer to. So here, let's now draw them. Divide and conquer. Let's now draw something for R and draw something for S, and then somehow we can make use of the epsilon transition to represent the plus. That's more or less where we're going to go. Okay? So let's say this. For R here, it's going to be some epsilon n of a. And remember the 3 bullet points, right? So just remember the bullet point here. These 3. Okay, just remember those 3. We're following them. Okay, so for R, it's going to have one single star states. And then it has also a single accept states. Let's start with that first. And then we also got S, which also has a single star states and also a single accept states. Okay? Let's say somehow we got R and we got S. But now, we want to construct the epsilon n of a for plus. How do we do that? Step number 1. You want to make all the accept state over here non-accept. Number 1. So rather than this, you're just going to draw a single circle without double circle, basically. It's really the same states. You're just making that from accept into non-accept. Number 1. Number 2, you're going to have a new star states right here. Just before I talk about it, for R and S, maybe this one used to be the star states, and this one also used to be the star states. But now we don't want these two anymore. Instead, we have a single star states right here. And that one there can either go to here, or it may go to here by epsilon. And then, from this n states and from this n state over here, you can simply take epsilon into a single accept states. That's how we do it. Let me recap very quickly, right? If you only talk about the epsilon n of a for R, it's going to be some star states, a single star states, and also a single accept states. Similarly for S as well. But now, if we want to construct something using the plus operator, we have to get rid of the star state here, and get rid of the accept state here, just make it regular states. And then we can do the purple part to concatenate, to really union them together. All right? All right, let's do something very similar. Okay? So now if I got concatenation, so I got R here, and also I got S over here. And again, it has a single accept states and a single a single accept states. And also here we got a single star states, and also we got a single accept states. So we got R and S independently. Now, how do we somehow do the concatenation, right? First of all, get rid of the start states and get rid of the accept state and make it regular. And also this one here, make it regular. Let's do that first. And then for the new epsilon NFA, we're going to have a single star states right here. And a single N states right here. Accept states, I meant, right here. And then, so this one here is going to go to the star state for R using epsilon. And from this regular states here, it's going to be connected to right here using epsilon. And then from this here, connect to here using epsilon. That's how we do it. Again, recap. If you look at only R and S independently to begin with, you have two separate star states, but that's not what we want. Also, you got two accept states. Also, that's not what we want. So that's what we want to do. Step number one, simply get rid of the start and also convert the accept into non-accept. And then we do the purple part, introducing one new star states and introducing one new accept state, and do the rest using epsilon transition. All right, so that's concatenation. Final one, about 0 or more repetitions, right? How do we do that? So for that one there, let's now start with R. That one there has a single star states to begin with. And also that one has a single accept state as well. Let's say here.
Sorry, the concatenation one, I'm a little bit confused. Like, I understand the epsilon between the accept state of R and the side state of S, but I don't think the epsilons between like
So that means if you're able to get to this state here, that means you have satisfied this pattern here and this pattern over here. So that means you have satisfied both R and S. So of course, you should be accepted ultimately without reading anything further.
It just in the slideshow, it didn't give the epsilons for, like, both in the slideshow and I think in the answers for the...
Maybe I'll check, but I should really go with what I'm presenting now. I can double check. Yeah. Okay, good. All right, let's say for the R star over here, okay? So if you want to specify 0 or more repetition, okay? Number one, we're gonna get rid of the star states right here and convert that into the regular state right here. Okay? 0 or more repetition. Okay? First of all, let's now introduce a new star states right here. And also we got some ending states, accept states basically. And this one here means 0 or more repetitions. Let's talk about 0 repetition. How can we specify a 0 repetition? That means if I'm here, I don't need to repeat anything. I can just go directly to here. A little bit similar to this. Okay? So I may go from here to here. Epsilon. That's a 0 part. And then if I want to go for as many more repetitions as I want, what I can do is, first of all, I might go to here, and then once I somehow reach right here, if I want to repeat more, I can just go back to the beginning state right here without doing anything. Okay? I can go back to right here without doing anything. And once I'm here, if I decide that I've done enough repetition, I can just go directly to accept. All right, let me recap. If you only look at R here, it has a single single start and single accept. 0 repetition simply means from the new start states, I go directly to the new accept states, repeating nothing. If I want to repeat once, I can simply go through using epsilon and go all the way from here to here, and then I can go to epsilon. That's one single repetition. If I want to get more than 1 repetitions, I can just go from the final state here back to the start state right here. Okay, so this is epsilon right here. 0 or more repetition. All right, so I would suggest that we do some exercises together. Yeah, just before we end the lecture today. Yeah, go ahead.
Given regular expressions E and F, in this slide are the regular expressions R and S?
Yeah, I like that. Absolutely. How about that? Thank you. Yeah, absolutely. All right, let's now try to do some exercises. Oh, wow, this is a complicated one, okay? So this one here, I will help you a little bit, okay? I think this one is really worth doing. I'll do part of it today. So let's say we do this one first? Let's break down one by one. Guys, how about we do this one first? 0 plus 1. How would you draw that? For this one, let's do it together, okay? For 0 plus 1. For 0 plus 1, first of all, let's draw the one for 0. And I'm just being a little bit more efficient because I know this is only part of it, so the start state and accept state will somehow be converted anyway. So let me draw them as non-start and non-accept to begin with. So this will be the 0 part. And I know that it's going to be plus, so I can draw them in parallel rather than one after the other. So this will be the 1. And then since I know it's going to be 0 or 1, so what I will do is I'm just going to have a new start state right here and a new end state here, but I don't really draw that as an accept state because I know something that's going to come after that. So this is not ending. So here I'm going to say this one here can go here, epsilon, or it can go here, epsilon. And here can go here, epsilon. And here can be here, epsilon. So think about this part here alone. This part here alone is the 0 plus 1. Okay? And now, the next part, let's now handle star. How do we extend the current diagram to say this particular 0 plus 1 may repeat 0 or more times? Okay? Well, we're going to apply, of course, the rule right here, right? This is only you guys' first example, so let's do it together. I'll just assign part of it as exercise for you. Bear with me, just about 1 or 2 minutes, and then we're done. Okay, for this one, how should we do it? This one here, for start, let's now draw the new start states right here, and also the new end states. And I know that after this, I still got more things to do, so I don't really draw that as a accept state just yet. Right? I'm just being a little bit more efficient. All right, 0 or more repetition. 0 repetition right here. And more repetition, right? So what we are saying is, you may go for 1 repetition. You just go here using epsilon. And then once you get to here, you can go for epsilon, go to here. 1 repetition. But what if I want 2 or more repetition? I can say, I can go from here back to here with no work, with no processing. Epsilon. So that part there is really the 0 plus 1 star. All right, so let me go. Okay, just give me 1 more minute. I'll make a remark, and then I'll assign something for you guys to try before Thursday. So I can think about this part here really is the 0 plus 1. All right, so before Thursday, I will highly recommend try to see if you can take this guy here and then do the rest. We still want to concatenate with 1 and also concatenate with 0 plus 1. Okay, I think we have done the most complicated part already. So you can give a try on finishing this diagram over here. And we'll go over the solution very quickly on Thursday as well. And then we'll go back to the epsilon NFA to DFA transformation. Okay, thank you so much, and I'll see you on Thursday.